Hi, I'm Chiara, and I'm a scientist building quantum computers. So here we are in my office at ETH Zurich, where I spent the last 4 years doing my doctorate researching quantum computing. When I was a little child, I was always really curious about nature and how things worked, why the sky was blue or why the grass was green. And that led me to study physics. And when I started studying physics, I then realized that quantum physics was really the most fundamental type of physics that I could study. And to me, it felt like I was really getting introduced in some sort of secret about life and the universe. And that's why I ended up doing quantum physics and quantum computing as my PhD.
Was fasziniert dich denn persönlich an der Welt der Quanten?
I find the world of quantum physics really fascinating because it's completely different from the world that we're used to in our everyday life. So, for example, if I try to go through this wall right now, I couldn't, obviously. I would stumble on the wall and fall to the ground. But if I were small particles, such as an atom or a photon or an electron, I could pass through the wall. And quantum physics is full of behaviors like this that are very, for us, difficult to grasp just because we're not used to them. And this is what makes it really interesting for me, even if, of course, it feels confusing and difficult to understand. And this was one aspect that made me really interested in studying quantum physics. And the second was that I felt that this quantum physics was really the fabric of reality. It was really something that is underneath everything. And if I wanted to really understand how life and the universe and the world around me works, that's what I should learn.
Was machst du in deiner Forschung?
I build some device that is used to hold individual atoms in space very carefully in a very specific location. So these devices we call ion traps, and the atoms that we hold in space, they are called ions because they are charged. So they either have 1 electron extra or 1 electron less. Because they're charged, then they can feel the effect of electrical fields. And so the ion trap is a trap to which we apply electrical fields, and these fields create really a cage for the ion. So the ion cannot escape from this cage, and it will stay in this location. And then using laser beams, we can then interact with the ion, and we can modify the internal state. And so my research is really specifically about designing and producing these ion traps.
Wie sieht dein Arbeitsalltag aus?
So a typical workday for me is not really typical. Every day looks different. There may be some days when I spend all day at my computer doing some simulation and calculations. Other days when I'm downstairs in the lab doing some experiments with the ions. And other days when I'm maybe in the clean room where I'm developing and fabricating the ion traps. So there's really a lot of variety within my week, and this is also one aspect that I love about this job.
Klassische Computer arbeiten ja mit 2 Zuständen, 0 und 1. Wie ist das bei Quantencomputern?
Quantum computers work by using the laws of quantum physics, and usually we use individual particles, for example in our case trapped ions, as the qubits. Using the qubits, we can then encode information in them and perform operations. What makes the quantum computers really special is that we can use these very unique laws of quantum physics to do calculations more efficiently and faster. And one of the key features of quantum physics is the fact that we can use superposition. I like to explain this using painting. So you can imagine that you're painting and you have 2 buckets of paint. One is yellow and one is blue. And now you can mix the yellow and the blue. You can imagine that you mix a little bit of blue in the yellow and you'll get a green, but you can also mix a little bit of yellow in the blue and then you'll get a darker green. So in fact you have the possibility of mixing in very different ratios so that you achieve a lot of different greens. Superposition works the same way. The yellow and the blue are the classic 0 and 1, 2 states, but in between them we can create a superposition, a mix of each one of the two, a mix of yellow and a mix of blue. And now because we have access to these extra states, then the operations and the calculations are much faster and more efficient.
Wie können wir uns diese Ionenfallen vorstellen?
An ion trap is a very small device that we use to hold the ions in space. And so let me tell you a bit how, for example, I would go about to build my own ion trap. So we start out with just some pieces of glass. And here, for example, I have one of these pieces. It's just a little piece of glass. And then we need to create electrodes. So these are usually, we do this by evaporating gold on the glass. And when we do that, then we end up with something that has these lines. Each one of these lines is an electrode. And now these lines, to these lines we can apply electrical fields. And now the electrical fields come to the ion and trap it in space. And so one of the things that we require to create these traps is, for example, one of such shadow masks. It's a metal sheet that we use to create the electrodes. And once the ion trap is built, how does it look like? So, for example, this is one of my trap wafers. And as you can see, it's just a very tiny wafer that is covered in gold. There are also many other ways to create an ion trap. And ion traps can also get very small. So, for example, this one, as you can see, is much smaller. Each of these traps can hold a few ions at a time.
Wie sieht dann so ein Experiment mit euren Ionenfallen aus?
The setup and the experiments are really complex and they're made up of lots of different parts. To be able to be sure that everything is running properly, we have to check every single item by itself, and the final check is whether we can trap the ion or not. Once we have a trapped ion, then we send a sequence of operations and calculations using laser beams on the ion. And at the end of the sequence, in order to see whether we actually performed the sequence that we wanted, we can shine a specific wavelength of light and see whether we see some photons emitted by the ion or not. And this is the way that we use to discriminate the state of our qubit, and it gives us an understanding of where the state ends up at the end of the sequence.
Es gibt ja noch nicht den einen Ansatz, wie man Quantencomputer baut. Worin bestehen die Unterschiede?
There's actually many different ways to implement a quantum computer and to build it up. The way that I'm researching is using trapped ions, but a different approach is, for example, using superconducting circuits. This is, for example, the approach that big companies such as IBM and Google are following. But until today, it's still very unclear which one of the different ways and platform will be the best one. Different platforms, trapped ions and superconducting circuits, they have their own unique strengths and challenges. Some of them make it easier for maybe one of them to scale up to more qubits, and the other makes it easier to get control over all the qubits at the same time. And so this is really an open field of research. We will get to know in the next few years which technology will make the cut.
Diese neue Technologie wird unsere Zukunft stark beeinflussen. Was sollten wir hier als Gesellschaft beachten?
By making sure that the access of the quantum computers are transparent and that all the governments and all the countries have access is, of course, one way to make sure that the introduction of quantum computers in the everyday life will be smooth. And the second aspect is to make sure that governments are ready well ahead of time for the transition from using quantum computing to do any kind of cryptography compared to classical. So as long as all the governments are ready to make this transition, this will be smooth and there will be ways to protect against any kind of attacks.
Und wie ist das mit Nachhaltigkeit? Verbrauchen diese riesigen Maschinen nicht sehr viel Strom?
So it's also fair to ask how much energy does a quantum computer consume? And actually there are some studies already based on the quantum computers of today, which are fairly small. Nevertheless, they give us a sense. For example, a small quantum computer today takes as much energy as a few kettles running. and this is even less than a car. So you can imagine that indeed quantum computers don't use as much energy as one would expect, even if there's a lot of hardware surrounding them, yet the energy consumption is not really an issue that we're worried about. Of course, as we scale up these systems, they will require more energy, but we're hoping that the ways that we use to scale them up won't require much energy. In fact, for sure it will be on the levels of a car. And so this is maybe surprising to some to hear. And for sure, I expect that, in fact, quantum computing will have a huge impact on solving some problems with how to find energy and renewable energies in the future. So I think that the impact the quantum computers will have on the whole field of energy production will be way more than the consumption that they actually have.
Warum sollten sich junge Menschen mit Quantentechnologien auseinandersetzen?
It's going to be really, pervasive as much as normal laptops and smartphones and so on. It's just great to be able to understand the world around you. To any young student that is interested in physics or quantum physics, I would say don't listen to anyone else, and if you're fascinated by this topic, just learn as much as you can about it and go for it. There's no other way to put it. If you really feel that you have a passion inside you, I just urge you to follow this passion, and this will take you to worlds that you can't even imagine.